And thus far, we've talked about launching those projectiles only in a horizontal fashion. Today, we're going to talk about launching those projectiles more at an angle, and what's the difference, basically. Again, our learning target, I will analyze projectile motion, understanding how gravity affects vertical displacement while horizontal motion remains constant, and apply these principles to predict the behavior of objects in motion. Okay, so just to review from the last lesson, the vertical and horizontal motion should be considered separately. Okay, gravity accelerates objects vertically downward, and the horizontal motion remains constant. Okay, that means it has a constant velocity. The time in both the vertical and horizontal motions is the same at all points in the motion. The range is the horizontal displacement of the object, and the height is the vertical displacement of the object. Okay, so these are all true for all projectiles. It doesn't matter, how they're launched. These are all true for all projectiles. But when we launch at an angle, what changes, right? Instead of launching it straight ahead, what happens if we now tilt that rocket and fire it up into the air? Okay, so what changes is the velocity. Okay, if you're now launching it at an angle, there's now velocity considered in the y direction, right? So the initial velocity is a vector and can be broken down into its component vectors, right? Remember, we use initial velocity as u. So u in the x direction is u times cosine of theta. U in the y direction is u times sine of theta. Okay, that's with the angle being between the trajectory and the ground, or the horizontal. Okay, so for example, a daredevil is shot out of a cannon at an angle of 45 degrees with an initial speed of 25 meters per second. What is the horizontal speed and what is the vertical speed? So the horizontal speed then would be 25, which is our initial velocity, times the cosine of theta, which is the angle, which is 45 degrees. And then the initial velocity in the y direction is equal to the 25, which is the speed of the trajectory, and then times the sine of 45 degrees. Okay, you can work those out on your calculator if you'd like, but this is the guts of it. Okay, all right. So just like in horizontal motion, the range is the horizontal displacement of the motion. We're just going to call that something different. We're going to call it delta x. Okay. The velocity is assumed to be constant, right? That means that it's not accelerating in that x direction. Okay. So just like with the horizontal, we had that the range is equal to the velocity times time. Here it's delta x, right? The displacement of the horizontal displacement is equal to that initial velocity times cosine theta, and then times time, right? So this is that x component of the velocity. Okay. The height is the vertical displacement of the overall trajectory, right? Last time we had it, the height was where was it being fired from? Like how high up, right? Well, now you can fire it from the ground, right? And it can go up into the air and then back down. So in this case, the vertical displacement is wherever the top of the trajectory is, right? Right where the velocity turns to 0. That's going to be your highest point, right? And the distance between that point and the starting point, or the ground, is going to be your height. Okay, so we assume that the object is accelerating due to gravity, so there's nothing else acting on that object, and that acceleration is constant. Again, remember, on Earth, that acceleration due to gravity is 9.8 meters per second squared. All right, here's where the change comes in. Now we have that our vertical displacement, or delta y, another way of saying that is the final y minus the beginning y, right? Where did it start and where did it end, right? At what height? In most of your problems, this is going to equal 0, right? Because you're going to start at the ground and you're going to end at the ground, okay? But now we have to put in that initial velocity component. So we have our velocity sine theta, that's our y component of the velocity, times t, okay? Then we're going to subtract 1/2 of the gravity, 1/2 of 9.8, times time squared, okay? So this is adding that velocity part to it, okay? You're also going to use the Subot equations. The two that really apply are that the velocity in the y direction is equal to the beginning velocity plus gravity times time, or you have the ending velocity in the y direction squared equals the beginning velocity squared minus 2 times g, 9.8, times the change in the distance, right? The displacement. Okay. All right. So knowing that, a lot of times what we really want to know is if we fire this object, right? If we launch this object, at what point is it going to be at its highest point? So the maximum height occurs when the vertical velocity is equal to 0. Okay, so if we go back here to our ending velocity squared equals beginning velocity squared minus 2 times g times the change, times the displacement, right? The vertical displacement. And you work that through, you get that the vertical displacement, the height, is equal to the beginning displacement in the y direction. So don't forget that this would be u sine theta, that whole number squared, divided by 2 times the gravitational constant. Okay, so let's look at a relatively simple problem. We have a daredevil is shot out of a cannon at an angle of 45 degrees with an initial speed of 25 meters per second. Excuse me. A net is positioned at a horizontal distance of 50 meters from the cannon. At what height above the cannon should the net be placed in order to catch the daredevil? So in this case, he's not going to finish his trajectory. He's going to fall into the net, which will be above the ground. Okay, so what that means is we know that the horizontal displacement, right, is 50 meters, because it's 50 meters from the cannon, okay, is equal to the initial velocity times the cosine of the angle, okay, times t. So in this case, we can solve for t by using the horizontal displacement. So you can see we're not always going to start with delta y. We do sometimes start with delta x. Okay, so when we do the math of this, we find that the time is 2.83 seconds. Okay, remember the time on the x in the x direction is the same as the time in the y direction. So I'm going to take this time and I'm going to substitute it for the t's that are in our vertical displacement equation. Okay, so I have our beginning u is 25. Now we're going to use the sine of the angle, so sine of 45. And then we're going to multiply by the time, so 2.83. And we're going to subtract 1/2 times 9.8 times that 2.83 squared, right? So if we do all of that math, we end up with the net needs to be 56.9 meters above the ground, okay? Always make sure that you understand what that means, right? Does it make sense that at 2.83 seconds, okay, that he will his height will be 56.9 meters. Okay, so at this point he's gone all the way up and he's starting to come down. Okay, okay, so to sum it up, we have again the vertical and horizontal motion should be considered separately. The time in both the vertical and horizontal motions is the same at all points of the motion. The initial velocity is a vector and can be broken down into its component vectors, x and y. And then the height is the vertical displacement, delta y, of the overall trajectory. This motion assumes the object is accelerating due to gravity and that it's constant.